Hello and welcome to T3 Day 10 of Honors Precalculus. We're going to continue talking about polar equations of conic sections. So we're going to determine the eccentricity, the type, and the directrix. That's all we need to find there. And then we can graph it using our Desmos or your calculator. Just use Desmos instead of Converge, which is an old program we don't use anymore. So right here in this equation, because it's cosine, we know it's going to go side to side. But immediately know that the e value is equal to 8 right there. So immediately know that the e value is equal to 8. And that means it's going to be 8 is greater than 1. Therefore, it's a hyperbola. So we know the general shape. We also know that because it's in the right form here, this is a 1 right here, it's in the right form. We know that this number, so 4, is equal to e times k. But we know that e is equal to 8. So we know that 8k is equal to 4. So in this case, k is equal to a half. This tells us, because it's going side to side, the directrix is a line, and it's going to be x is equal to, going back to what we looked at before, those four statements here. The slight difference being you have the plus right there, the minus right there, the plus right there, and the minus right there. So the one we're looking at is this one right here, this right here. The k is the distance from the directrix to the focus, and because it's minus e cosine theta, which is the form of the question we're at, the directrix is x is equal to negative k in this case. So what that means, going back to our first equation, we have a minus sign right there. So that tells us that the directrix is going to be x is equal to negative 1/2, because in this case it's minus. If it was plus, it'd be x equals a half. So when you graph this on your calculator, you're going to get something like this right here. Remember that the origin is right here, and that's also in the focus, and then this right here, x equals negative a half, that's your directrix right there. So it's pretty close, so it's going to be it's going to be pretty steep like this, pretty steep, and you can use Desmos or your calculator to get this graph. But the key thing to realize here is because it's cosine, it's side to side, so it's going to be x equals, and because it's minus here, it's going to be minus right there. So if it was plus, it would be plus a half. It would be on the other side. So on the next one right here, the key we have to realize is that 4 here has to be turned into 1. So what we're going to do here is we're going to multiply this by 1/4 and this by 1/4, which is a fancy form of 1. So with r is equal to 6 times 1/4 over 4 times 1/4, we have to distribute minus 3 times 1/4 sine theta. So this simplifies to 6/4 is 3/2 over 1 minus 3/4 sine theta. So that immediately tells us that this right here is the e value. So e is equal to 3/4, which is less than 1. So this is going to be an ellipse right here. So then we also know it's going to go up and down because it's sine. It's going to go up and down because it's sine. And we know that this right here, the top, so 3/2 is going to be equal to e times k. So when we do this, you end up with 3/2 is equal to 3/4 times k. So you multiply this out and you end up with 3/2 times 4/3 is equal to k. So you get k is equal to 2. So in this case, because it's a minus sign right there, we know that the directrix is going to be y is equal to negative 2. So when you graph this out, it does end up looking like this wonderful vertical right here. The directrix, it will be at negative 2, so y is equal to negative 2. Focus is here, and it goes up, and it goes up. But you're going to use Desmos or your calculator to generate these graphs. So let's find a polar equation of a hyperbola, and it gives us the focus at the pole, which makes our math easier, and negative 3,0 and 1.5 pi as endpoints of its transverse axes. So again, we end up with this equation: r is equal to ek 1 minus e cosine theta, and we know that because it gives us the 2 points for the endpoints of its transverse axes, which is where the vertices are going to be. So this point right here is negative 3,0 right there, and that point right there is 1.5 comma pi, like this. Remember, those are in polar form. So what that means is, since those are the ends of the transverse axes, you know that this thing is roughly going to look like this. It's roughly going to look like this. So that means it's going side to side, and the directrix will be to the left, to the left of the origin, so it'll be minus. So that's why we know it's of this form right here. So we know, for example, when we plug in values, for example, 3, 0 right here, if we plug in 3, 0, we know that negative 3 is equal to ek over 1 minus e times cosine of 0. And cosine of 0 is 1, so we end up with negative 3 is equal to e times k. Sorry, I got to put this as a numerator here. So numerator is going to be e times k over 1 minus e, like this. So that's one equation, right? But then we also have this point right here, 1.5 pi. So we know that 1.5 is equal to ek over 1 minus e cosine pi. Well, cosine of pi is just 1. So we end up with 1.5 equals e times k over 1 minus, cosine of pi is negative 1, so this turns into plus e right there. So when we cross multiply, we end up with 1.5 plus 1.5 e is equal to ek, like this. And if we cross multiply over here, we end up with negative 3 plus 3e is equal to ek. Well, you'll notice that we have e to the ek and ek right here. So what that means is we can take these two things right here. We have negative 3 plus 3e is equal to 1.5 plus 1.5e. We can collect like terms, and we have 1.5e is equal to 4.5. So e in this case is equal to 3. It's always a good sign when you get that. So now we can solve for k in a bunch of different ways. So one way we could do that is we can just plug it in up here. So we know, for example, now that negative 3 plus 3 times 3 is equal to e times k, like that. So that means that 6 is equal to e times k. So we could also plug in 3 right there, so k would be equal to 2 in this case, which kind of makes sense because it's in between. It would be the directrix would be x is equal to negative 2. It doesn't ask that, but you could do that. But to find this equation now, we now know that ek is equal to 6. We know that e is equal to 3. So our equation is going to be 6 over 1 minus 3 cosine theta, which is pretty cool. So then you can plug that into Desmos and you get a cool graph that looks just like that. So you might be asking yourself, well, how do I graph these by hand if you give them in polar form and I don't want to plot out points? The simple answer to that is we're going to learn how to convert these into Cartesian coordinates. So let's take a look at this one. We're going to analyze this conic section. So we know this goes side to side because it's cosine, and we know the directrix is going to be to the left of the origin because it's minus right there. So we automatically need to turn this into the right form, and we're going to do that by, we need to turn that leading number, that 5, into 1, right? So we multiply this by 1/5 over 1/5, which is a fancy form of 1. So we have r is equal to 16 over 5 over 1 minus 3/5 cosine theta. That's nice because it tells us that the eccentricity is going to be on this one 3/5, which means it's an ellipse. So that tells us it's an ellipse. That's pretty cool. So now what we can do is try to write our equation. And when I say try to write our equation, we're trying to do that by writing it out in Cartesian. And that's what these values are right here, the Cartesian form. So how do we do that? Well, we know that the way this is set up is that it's going to be an ellipse with a focus at the origin. So we know one of the foci is right here. We know that the directrix is to the left. What we can do is we can plot some points to help us out a little bit. So for example, when theta is equal to 0, so when theta is equal to 0, we're plugging in 0 in for theta right here. When theta is equal to 0, it's 16 over 5 over 1 minus 3 over 5 times cosine of 0. Cosine, when you do this out, or you can do the original one too, it doesn't really matter. You can plug it in up here. You end up with r, when it's 0, is equal to 8. So what that means is out here, there's a point at 8, 0 in Cartesian land. What you then can do is you could also do pi, so r of pi. And when you do that, you can plug it into the original this time, it's fine. You don't have to do that divide by 5 thing. So it's gonna be 16 over 5 minus 3 cosine pi. Well, that's 3 cosine pi is -1, so you end up with 8 on the bottom, so this is equal to 2. So what that means is when you have a theta value of pi, so theta value of pi is there, remember that's pi, it's going to be 2 away, so it's going to be right here at -2. So then we have our ellipse here, and everything is symmetric here. So we know our center is going to be right in between these two. So if that's -2 and that's 8, our center right there, center is going to be at 3, 0. That's halfway between the two. That's halfway between the two. So I'll label it right here. So this is our center at 3, 0. So let's say we wanted to know the height here. If we wanted to know, like, how high does it go? We'd want to know how to get, like, if on here, where does the ellipse cross? That's what we need to find next, which gives us the other axes. Well, we can't really do that by plugging in an angle value, but we know that the eccentricity on this, the eccentricity of the ellipse, the eccentricity of the ellipse, as we write it, is c over a. So we know that the ellipse overall has, it's the same eccentricity here, so that 3/5 is equal to c over a right here, and we know that a is equal to 5. That's the side-to-side distance, so 3 to 8 is 5. So what that tells us in this case is 5c is equal to 15, so c is equal to 3. So what that means is we now know for our ellipse, we know that c squared is equal to a squared minus b squared. So we know that 3 squared is equal to 5 squared minus b squared. So we know that 9 is equal to 25 minus b squared. So we end up with -16 is equal to -b squared. So b squared is equal to 16. So what that tells us is that b is equal to 4 in this case. So that means you go up 4. You go up 4 here. So this one's going to be 3, 4 right there. And this one's going to be 3, -4. So what we have here is we have our ellipse. Here's our ellipse. We've drawn it out. And now we can easily write the equation, because from the polar we were able to get the center and then plot a couple points to get two opposite ends, and that gives us our a value. So we end up with this x minus 3 squared over 25, because that's a squared, plus, because it's an ellipse, y minus 0 squared. I'm just being overly complete here, over 4 squared, which is 16. I'll just write it as 16, and this equals 1. So this allowed us to find all of these things. So we found E, A, B, and C. One thing you will have to do is write out all of the vertices in polar and Cartesian form. The ones we found over to the left were in Cartesian form. So you have these points here. You need to remember how to convert between the two. You need to know how to convert between the two. So it's the distance from the origin, and then the angle measure, it scoops out from the positive. Remember, the angle is from here to there. So if the point is there, this is the theta value from the positive x-axis. These polar coordinates come out to be these 2 comma pi. We did those two. These are a little bit more decimally because you have to use your calculator to calculate them, but you end up with this right here. And this is why we didn't use them to begin with, but you need to be able to convert between the two. So if you need to go back and study that, you should. But the key thing you remember is the relationships are r squared is equal to x squared plus y squared. And we know that tangent of theta is equal to y over x. So then theta is equal to tan inverse of y over x, which is what we used to find those values right there. So again, you can do this piece by piece. The new thing for this one is you can plot these points. So when we did this right here, that allowed us to find the -2 and the 8. And then that allowed us to find the a value, which gave us the c value, and then we plugged it in to find the b value. And when we have all those values for an ellipse, we can write it in Cartesian form, which is right here. When we have it in Cartesian form, we can graph it by hand pretty accurately.